When you first hear about alternative energy, the first thing to most people's mind is solar photovoltaics or solar panels like we have here. We're on top of Building Q at Southern Polytechnic State University, and we're generating power up here to help augment the power in this building. The most important part of solar power generation, though, is the humble solar cell. If we look down here, we'll see panels are actually made up of individual cells, and these cells are tied together with conductors in order to build up the voltage high enough to deliver power to the building and to the equipment over on the other side of the building. Today we're going to be visiting Dr. Deidre Hodges in her lab, where she's creating a whole new type of solar cell. I'm Scott Tippins, and this is the Energy Hunter. Let's take a quick look at how a solar cell works before we go visit the lab. To help me along here, I've got an assistant that's going to help draw on the board. You ready? Good. Okay. Now, solar cells function based upon a simple physical principle called the photoelectric effect. We can think of the sun as having photons, basically particles of light, coming down and streaming to the earth and hitting all the material on the earth. When a photon actually strikes an atom, it can force, if it has enough energy, it can force an electron to be released by the atom and can be used in circuits and other things. All materials have the potential for absorbing photons, but we have to have a special material in order to capture that electron and then use it to generate energy with. There are two fundamental materials necessary for a solar cell to function properly: an N-type material and a P-type material. By themselves, these materials are not all that special, but when they're located next to each other, something very interesting happens. A special zone forms at the junction of the two materials called the depletion zone. Because of this junction, electrons ejected from the material by photons can be captured and turned into electric current. But that's not enough. We need to be able to conduct those captured electrons away from the cell and into our circuit. Typical solar cells have a metal backing on the P side and metal fingers on the N side. These allow cells to connect to one another or to a load such as the lights in your home. Another way to look at the solar cell is it's a battery with a plus and a minus side, and that's how we build up voltages in our solar panels, is by connecting them just like you would in a flashlight, putting the batteries one behind the other. Deidre Hodges cells are going to be a little bit different than the cells that we've looked at here. They function primarily the same way. The difference is the types of materials that she's going to be using. The material she's using is called CZTS, and that basically stands for copper, zinc, tin, and sulfur. Most of these are earth-abundant materials, which make this cell a lot cheaper to manufacture, and it's fairly low toxicity compared to some of the other cells that people are researching to cut down on cost. So let's go take a look in the lab and see what she's doing. Guys, we're here with Deidre Hodges in her lab. She's actually single-handedly creating a solar cell fabrication lab, state-of-the-art, here at Southern Poly. Now, we don't have everything, but she's building it up as a piece at a time. You want to tell us a little bit about what you're doing here?
Sure. We're doing research. We're fabricating thin film solar cells, and we're using green renewable materials, non-toxic materials.
Very cool.
We're using copper, zinc, tin, and sulfur.
Very cool.
Current thin film technologies today, they use materials in their solar cells that are expensive,
right,
that are rare in the Earth's crust,
okay,
like And they're also using some toxic materials.
That's what I had heard. Yeah,
Yes.
sometimes there can be some bad stuff in there, and we want to prevent that. So you're trying to find a way to make this green,
Yes.
make
Yes.
it more
Yes.
good for the environment and generate energy. That's a
Yes,
pretty
yes,
amazing
yes.
trade-off, actually.
Yes,
That's
yes.
fantastic.
And so it's a lot of chemistry, a lot
Okay.
of processing, finding the right processing conditions.
Okay.
And with these particular materials, copper, zinc, tin, and sulfur,
Fantastic.
to get the right electrical properties
And you test
for
those.
this device.
So after we've finished with the annealing thing, you go through and you do some testing and you get data on the electrical properties.
Yes.
That's right. Okay.
Yeah.
Yeah.
So, Manoj,
Yes, sir.
you're working on what here?
I'm trying to deposit material on my glass substrate right now.
Okay, all right.
And then
So you're putting some material on there,
onto the glass.
and that material is going to be used in one of your solar cells?
Yeah.
Okay, so it gets clean first?
Yeah.
So he's just using a little methanol to remove contaminants
All
to
right.
help with adhesion.
Now, when you say help with adhesion, you're hoping the material bonds to the glass? Is that right?
Yes.
Okay.
Mm-hmm.
And this is the material that will eventually become a solar cell, right?
Yes.
Yeah.
Okay.
One of the layers.
One of the layers. Okay, one of the layers.
And one of the importance of cleaning is it'll form a smooth surface.
Mhm.
And it'll form the bond better, and the material sticks on the surface better.
Okay, well, excellent.
Yeah, once we add our methanol and water to clean our substrate, come over
You
here to air dry.
air dry it?
With
Okay.
nitrogen.
With nitrogen.
Nitrogen gas.
Of course, nitrogen is perfectly safe, right?
Yes.
It's an inert gas, so no worries there.
Yeah.
Why do you choose nitrogen instead of air? I mean, what's the difference between the two?
Air, compressed air
Right.
has oxygen, so if we leave the oxygen, that's reactive with our material.
Oh, okay,
It becomes
excellent,
a
okay.
defect,
All
so
right.
we'll use the nitrogen.
So it's about keeping this pure.
Yes,
And,
yes,
and,
like in
and
a clean room.
like in a clean room.
Yes.
Yep. Okay.
Yeah.
All right. The only one in here without a coat's me, so I hope I'm not contaminating the whole shebang here.
No, no.
Okay, wonderful.
Okay.
All right.
Okay.
So what's happening on this side?
We have a plastic.
Plastic.
It has
Okay.
a sticky surface on top.
All right.
And what we do is we put this glass substrate on top of it,
Uh-huh.
right in the middle.
All right.
So that
So that's going to go into the machine here,
yeah,
and you're going to be putting material on top of that
yeah,
by using this.
yeah.
Okay.
A vacuum spin coater,
Mm-hmm.
and when we turn on the pump.
Right.
So it creates a suction from
Okay.
the bottom. So when we turn on the pump, you can feel the air right here. It sucks the material at the top.
Oh,
So
yeah, no,
when
yeah,
it
I got that.
And it spins at two different RPMs. One is right now it's at 200 RPMs,
200, okay.
and then it goes on to after 20 seconds it moves on to 800 RPM.
Okay.
So it does that for 20 seconds. On
So
each RPM.
it's getting slower,
no, it's going fast.
getting faster.
Yeah.
Okay, getting faster.
Now we're ready for spin coating. Now we get our stuff from there.
Okay.
Whatever we are spin coating on top of that.
All right, so we're gonna go get some material because you're experimenting. You're trying to find the absolute best thin film material to use, right?
Yeah.
And so this is part of the experiment. You created this. You've mixed
Yeah.
different chemicals.
Yeah.
It looks like the liquid's moving in there. What's going
Yeah.
on?
Actually, the machine inside has a magnetic spinner.
Okay.
It keeps on spinning us at certain RPMs. Right now, it's spinning at 800 RPMs.
Okay.
And
So
then the temperature here is 120 degrees.
so there doesn't have to be a stick or anything in there moving it around.
No.
It's
It's
just a magnet that's running around underneath this
Yeah.
thing, causing it to spin the material.
Yes.
That's pretty cool.
Yeah.
You think we could put that on my oven at home, stir my soup while I'm cooking, right?
Yeah.
I mean, wouldn't that be awesome? Huh? So I could have an oven that's this is a proprietary idea that we've come up with here on the Energy Hunter. So a self-stirring soup pot pan system. Okay?
Yes.
So you heard it here first. All right.
So we have a temperature thermometer right there, and it shows
Cool.
almost 55 degrees.
All right.
And what we do is we absorb some material now. So we got some.
All right. And we're going to carry this over to the spinner. All right. All right. So that thing in the middle, we just taped down with a vacuum or held down with a vacuum.
Yeah.
Our little glass piece
Yes.
is now going to start spinning inside this.
Yeah.
Okay.
And then once we hit run, it's going to take a little time to stop moving.
Okay.
So once it just starts moving, we drop our material in there.
All right, wonderful. Oh, look at there.
Right now it's running at 200 RPMs.
200, right? And so it's spinning out the material and laying it flat, getting a nice smooth, even surface.
Yes.
Is that the whole
Yes.
idea? Okay. You know what this, oh, there we go. Wow. That really, okay. Now that, didn't expect that one. That's pretty awesome. You know, this is kind of like my daughter's little painting thing. Have you ever seen those? You know, you drop it down there and it splatters the paint everywhere. That's what's kind of going on in here. That's awesome. So we have a solar cell, right? No? Is this a solar cell?
The
P
version of the solar
The
cell.
P version.
Just
So we have half of the cell.
Yeah, half.
So we've created half of the cell so far. Wow. That's a whole lot different than when it went in, isn't it?
Yes.
Okay. That's fantastic. Now what do we do?
We let it air dry for like 5 minutes.
Okay.
And then after it air dries it, and then we take it over there and heat it up at 300 degrees centigrade for like 10 minutes.
Okay.
And then after that, we're ready.
So that's what you call the anneal. You carry it over and you do the anneal.
No, that's just a.
No, that's just a heater.
Heating
Okay,
of
a
the
heater.
oven.
All right.
Just put it in a petri dish and put it on top of the
Okay.
heater.
All right.
And then after that, we're ready for annealing.
Okay.
So whenever we have time, we anneal after that.
So the air drying is finished,
Yeah. For 5 minutes.
and then you put it in. So
On top of this.
so this is what we just created with our little spin machine over there, and then you put this on there, and that's a heater.
Yes.
And so you're going to heat that a little bit. It's different from the annealer,
Yeah.
okay? But the heater actually is going to heat it up and dry it. Okay.
It's just trying to dry it.
Okay.
Before we, like the main problem with annealing directly after air drying
Right.
is like it'll be too much temperature, so that it'll create a lot of stresses on it.
Okay.
So we give a toast of the heat before we anneal.
All right. So you're just trying to kind of ramp it up slowly, not
Yeah.
just all of a sudden throw it in there and just really hot. Okay. Yeah. That's pretty good. All right.
That's the reason.
That's very cool. So you're going to show us what is it, how to do an anneal? Is that right?
Yes,
Okay.
yes.
What does it mean to anneal?
The point of annealing is to remove the impurities
Okay.
in our solar cell, and also to release stress in the solar
Okay.
cell. So
So what do we do? What does the anneal machine do for us?
it warms our thin film to a high temperature and releases the impurities in it. That's
Okay.
what it does.
Awesome.
All right, so first we'll put it on the dish. Cover that up. We'll open our furnace.
Mm-hmm. Ah, there's a furnace in there. Okay.
Yes.
So does anybody cook lunch in there? I mean, is that, you get a little hungry, put a burrito in there maybe?
Nah,
No?
it's a little
Okay.
too small.
All right.
It's a little too hot in here.
It'll be a quick cook burrito,
Yeah,
right?
it will
There you
be.
go.
Now
Awesome.
we'll program it. And for this anneal, I'm going to do 30 minutes today.
Oh, okay.
At 550 degrees.
550 degrees. Wow.
Yes.
That amount of heat is going to do what to our sample? It's going to, you said remove impurities, is
Yes,
that right?
It's going to warm it. We're basically trying to find the right temperature.
Okay.
That's going to give us the highest efficiency in our solar
Okay.
cells.
Awesome. So what do we do after we finished annealing?
Annealing, we
Test the
on
material.
the scanning electron microscope,
Okay.
and then
Do we have one of those here at Southern Poly?
yeah.
Wow. A scanning electron microscope at Southern Poly. Whoa. Is that amazing?
Yeah.
So do you have a picture that we can see that you scanned of one of these cells? We've got a nice picture here of a scan of one of those things we just created after it was heated and prepared for creating a solar cell. Very cool. Now, I got a couple of questions I want to ask
Okay,
you.
all right, good.
This
good.
big thing, this behemoth thing that's sitting right behind us here, it looks really expensive and it also looks amazingly high tech. What does that do?
This is Hurt J. Lesker's physical vapor deposition system.
Okay.
And this is a system that will allow us to sputter, deposit the materials.
Isn't that kind of what we were doing over there when we were doing the spinny thing?
Yeah.
This is the kind of
we're doing it in vacuum.
Ah,
And then,
okay.
as opposed to mixing the chemicals in a solution and
Right.
then depositing them, we'll be getting the elements through sputtering. Argon and a gun
you'll
will
just put 'em
knock
in-
off a material
So you'll cut out a lot of the process you've been
Yes.
going through so far
Yeah.
and doing this.
and do it all in vacuum. We'll do it
This
all
is
in
this
vacuum.
is like the Ferrari.
Yes.
You guys are now running with the VW Bug.
Yeah.
This is the Ferrari,
Yes.
okay, or the Maserati. This is going to be
Yes.
amazing.
Yes, yeah, and then not only will we be using this for solar cell research, but other scientists and researchers will be able to use it for materials for their devices.
Anything that requires
state-of-the-art
sputtering of material
materials.
on a substrate.
Yeah.
That's
Yeah.
fantastic.
Yeah.
Well, I want
Electrical
to ask you about
devices.
something else over
Okay,
here. This
sure.
is really cool. So what is all this? What are all these little things in the boxes here? I mean,
These are exactly what you've seen them do. Those
Right.
are thin layers of the CZTS,
Okay.
the main layer of our solar cell. Thin layers of the copper, zinc, tin, and sulfur. These were initially deposited before the spin coater. These layers are where we just dip them into the solution.
okay, so you just
Yeah.
dip them in and then you got
Then
that.
dried it, yeah.
And
Yes.
why are they in different colors? Why is there so many different colors here? We got,
Different thicknesses
okay,
and different recipes.
okay. all right.
Different recipes.
So you're trying to, it's like you're trying to find the best recipe for pasta sauce, right?
Yes.
You're mixing
Yes.
different things and
Yes.
and if it gets just right, it's going to be a great energy
Yes.
generating phenomenon.
Yes,
Okay.
exactly
all right.
right.
Fantastic.
Exactly right.
Now tell me a little bit about the other things that you're doing, because I know this is not the only thing we're doing with the lab. You're planning some more stuff, right? So what
Yes.
other things are we planning for the
Yes.
lab?
Currently, we have a proposal that's submitted to get more equipment in. So
Okay.
this is part of the process where we fabricate the materials.
Okay.
So we've built up to this stage where we can make the devices, make the materials.
Right.
The next step is to measure, to see how well we did.
So some measurement instrumentation.
Measurement instrumentation.
Ah,
So
okay.
we have a proposal currently submitted, and we're waiting to hear if we are awarded this proposal. We'll begin to get in the measurement equipment, the instrumentation,
Okay.
to
Okay.
evaluate how well we're doing.
So basically, if those people are watching now who are making a
Yes.
decision about this thing,
Yes.
if you want to change the world, completely change the world, and you want to create a cell that's environmentally friendly and highly efficient,
Yeah.
give her the equipment she needs.
Yeah. Yes.
All right? Okay.
Right.
Fantastic.
Right, and we'll be writing more proposals to get more funding in
Okay.
the future to continue with students.
All right.
And to have additional students in and continue doing the work.
Oh, I think it's fantastic what
Yeah.
you're doing. You've got all these students in here. They're now energetic and they're ready to go into science and they're getting this laboratory experience. That's exactly what it's supposed to happen in college, right? You're
Yes.
supposed to come and
Yeah.
get this experience in the lab. This is fantastic. Can I be a student?
Yeah.
Can I get a lab coat?
Sure.
Get my own lab coat? I would
Sure.
love to do that.
Sure.
Oh,
And our students are getting hired and going on to graduate school just as soon as.
isn't that the problem
I
though?
get
You're
them trained.
losing
That's a
all the,
problem.
yeah, you get
That's
them
a
trained, they
problem.
go
I get
off
them
and they're,
trained and they go off.
you guys go off and get jobs. What's the deal?
It's great for
Huh?
them.
I don't understand. Why not stay here? Make a difference. Okay.
Yeah.
Well, thank you very much.
Thank
This
you.
has been an installment of the Energy Hunter. We visited Deidre Hodges, Dr. Deidre Hodges here in her research lab as she creates new and exciting thin film solar technology. We'll see you next time on the next episode. Just about every panel you see on campus is a silicon-based photocell. It's not a photocell, it's a solar cell. Okay, now that we understand you can't look at the floor. You can't look at the floor. You're looking at the floor. Okay, now that we understand how a basic solar cell is constructed, the basic parts, let's talk about don't laugh.